Hello, welcome to today's webinar, Best Practices for Membrane and Biphasic In Vitro Dissolution with DDD Plus and GastroPlus. Due to circumstances beyond our control, Jim Mullen could not be with us live today. However, he has provided his presentation, which we will play in a moment. The audio will play through your computer speakers, so please adjust your volume. The Q&A portion of our webinar will be handled by Chief Scientist Vera Lukachova. Thank you all for being here. We take your privacy rights seriously. By attending this event or participating in the Q&A session, you are allowing us to contact you for follow-up. You may submit questions at any time during the presentation. If you need assistance during the webinar, please use the hand raise icon and our staff will assist you. Without further delay, we'll begin the presentation.
Hello, everybody. My name is Jim Mullen. Today, we're going to be talking about the best practices for membrane and biphasic in vitro dissolution with DDD Plus and GastroPlus. What is DDD Plus? It really allows you to reimagine the design and analysis of your in vitro dissolution studies. It's now utilized by 50 plus companies globally
I'm
and the
sorry,
US
but
and
we are
China
not hearing the
FDA.
sound from
It
the
provides model
presentation.
for most dosage forms and experimental conditions, immediate, delayed, controlled release oral products, along with long-acting injectable formulations. It allows you to look at the dissolution in a variety of apparatus like the USP, ASD, biphasic, and membrane dissolution apparatus. There's significant momentum behind the merge of DDD Plus and GastroPlus for capturing IV-IVE of precipitation kinetics and establishing product specifications. So first, I'm going to go through a high-level introduction on what I'm going to be talking about today. So first off, we're going to give a high-level intro on DDD Plus. How can it be utilized in drug development? What can DDD Plus predict? What inputs are necessary? And what results can be obtained? And then second, we're going to go through a case study that looks at the synergy of DDD Plus and GastroPlus. We're going to look at biphasic and membrane dissolution experiments for the determination of in vitro precipitation kinetics. And then we're going to use those in vitro precipitation kinetics to do IV-IVE extrapolation into human using GastroPlus. So really the linkage of the in vitro experiments to the in vivo predictions in GastroPlus. So how can the simulation software be used? Well, it can be used for dissolution method development. So you could ask a question, how can I design my in vitro experiment to correlate with the in vivo release? And so if you know how if you're able to deconvolute the in vivo release profile using our Gastro plus IV-IVC module, and you know what your in vivo release is for your drug product, you can then see how you might modify your in vitro experiment to match that in vivo release. So how might I tweak the buffer parameters, the pH of my experiment? Maybe I need to make it a biorelevant media or whatnot. How can I get those to match up accordingly? And then you could also use it for formulation design. How do I modify the formulation ingredients to produce a desired in vitro dissolution rate that meets my target? And you can further specify how that target dissolution rate is going to behave in vivo with the combination of GastroPlus using the IV-IVC module. You can also establish or design safe spaces. So you can look at the content uniformity around your tablet ingredients. In this case, it's sort of a canned example about how you might modify the HPMC content or the variability in your HPMC content, how that affects the high and low end of the dissolution specifications. And so you can then take that high and low end of your dissolution specifications and rationally predict what will happen in vivo using GastroPlus. You can see how the plot on the right, we feed those high and low dissolution rates into GastroPlus simulator. You can also use the population simulator, look at the population pharmacokinetics, and really assess the bioequivalence between the high end and the low end of the dissolution specifications. What does DDD Plus consider? Well, DDD Plus is a state-of-the-art formulation a simulation program that allows you to look at all the equations that account for dissolution rate of active pharmaceutical ingredients and the excipient. So it not only simulates the release of the API, but that of the excipients as well. You can look at the particle size distributions for the API and excipients. There's a variety of dosage form models you can look at. So we'll talk about that here in a few slides, but both IR and CR products are simulated. You can look at the dynamic microclimate pH around the surface of your crystal or your excipients. So we have a very complex set of pH equations that are calculated that look into the concentration of all acids, bases, and salt equivalents and really come up with the pH that's at the surface of the crystal in your formulation. There's also various USP or biorelevant experimental apparatuses, and we can take into account surfactants in the media, both biorelevant and non-biorelevant. What inputs do you need for the DDD plus simulation? You need to know the formulation inputs: compression force, tablet diameter, disintegration time for an IR product. So if you have a disintegration tester value for disintegration, you could add that. You need to know the porosity and the matrix dimensions for the CR dosage forms. And then you need to know something about the physicochemical properties of the API and any excipients. Of course, we have a large excipient database, but if you have any new excipients, you're going to need to supply the information. And for the API, you're going to need to know the name of the ingredient, the whether it's the API, wetting agent, disintegrant, solubilizer, or some kind of other ingredient or filler. Salt type, molecular weight of the ingredient, the diffusion coefficient of the ingredient, the pKa's of the ingredient, so what ionizable groups are on the molecules and what pKa value that is. Solubility factor, which is the ratio of the charged form solubility to the neutral form solubility, the solubility at reference pH. So that is an important aspect that helps determine the full pH solubility profile along with the pKa's and solubility factor. You also need to know the particle size distribution, so the mean or standard deviation and the number of bins to simulate. This can be extracted from laser diffraction particle size distribution data. Then you need to set the apparatus information or the dissolution method, so the vessel type, the speed at which it's operated, the initial pH, the media volume, the buffer concentration, any surfactants that are in the media, or any different dissolution phases. So if you have a gastric to intestinal buffer transit experiment, you need to specify those phases of the experiment in the software. Important note is that you need to apply wherever possible in vitro dissolution data to optimize some key parameters first in developing and validating the model. So you at least need to take usually one data set for your tablet formulation to optimize the model to get that model to properly predict your formulation. Then you can use it to extrapolate to other scenarios. Of course, we don't have mechanistic models for how things like ribbon density and in the granulation process or wet granulation parameters affect dissolution. So there is a calibration step that occurs when building these models in order to match in vitro data. The formulation models I mentioned for immediate release, we have IR powders. We have solutions for precipitation studies. We have tablet models, capsules, bead coated, so IR bead coating. We have a delayed release formulation for a pH triggered coating around a tablet. We have a controlled release model for polymer matrix swellable and non-swellable. These would be for typical matrix tablets. Bilayer tablet for the combination of an IR tablet and a CR matrix tablet. We have CR bead coating, and then we have a long-acting injectable microsphere model. The experimental apparatuses, or apparati, I guess, if you will, that we have in the DDD Plus model are the USP1 basket, USP2 paddle. We have the USP4 flow-through and open or closed loop configuration. We have the intrinsic dissolution method as well. Pion microdisc profiler, artificial stomach duodenum test, membrane dissolution, and biphasic dissolution, which are highlighted red here because that's going to be the focus of our example here today and what we're going to show in this webinar. We've improved the multi-stage dissolution experiment functionality in GastroPlus. So that allows you to quickly redesign your in vitro experiment to help when you want to, more accurately produce a in vitro to in vivo correlation. So if you need to adjust your in vitro method to have a multi-stage dissolution that will more better simulate the in vivo condition, you can do that with our multi-stage dissolution experiment. So DDD Plus allows you to optimize how you set up your multi-stage dissolution experiments, look at instrument speeds, volumes, pHs of each phase, and allows you to look at the full buffer composition in each phase and how those buffers mix together when you go from the gastric to the intestinal phase. If you use 4x concentrated FASF buffer to equalize the pH to 6.5 when you mix that with the hydrochloric acid, our software now predicts that and allows you to do that fully mechanistically using our pH buffer calculations. So it really does an excellent job of combining all the aspects of the pH model in DDD+. The outputs that you get from the simulation are the dissolution profile for all formulation ingredients shown on the upper left, the media microclimate pH changes, which is shown on the upper right. You can do parameter sensitivity analysis. So if you have different doses, different amounts of some excipient, different particle size, you can look at the effects on the amount released versus those key variables. You can look at F1 and F2 similarity calculations. And then finally, the virtual trials functionality, which is smack dab in the middle here. And that allows you to look at the high and low end of the predicted dissolution specifications based on content uniformity or variability in the manufacturing process of the API, things like particle size distribution. Very important feature that allows you to look at the likely variability. So today I wanted to talk about a case study that highlights the synergy of GastroPlus and DDD Plus together. It's going to leverage DDD Plus to determine the dissolution and precipitation kinetics for dipyridamole, ketoconazole, and itraconazole. So in this case, we'll be able to predict the precipitation parameters for each of these compounds. And for the case of itraconazole, where there's some excipients involved, we'll be able to look at the differences in formulation solubility based on the membrane or biphasic dissolution apparatus. To do that, we're first going to look at the theory of membrane dissolution, biphasic dissolution, precipitation modeling, and then we'll look at how we built the DDD plus precipitation model for our case study for the biphasic and membrane dissolution. We're going to then use GastroPlus to predict in vivo PK with the DDD plus precipitation kinetic parameters that we obtained from DDD plus for dipyridamole, ketoconazole, and itraconazole. So that'll be how we wrap up the presentation today. So the membrane dissolution experiment, just a high-level overview. It's a dissolution tool that's useful for assessing formulation solubility for amorphous or enabled formulations versus crystalline drug. If the dissolution rate is not the limiting mechanism, it allows you to look at the free drug in solution, because that's the driving force for the permeability of the drug through the membrane and into the receiver solution. So it can directly assess the solubility of the formulation. Also, it allows you to fit precipitation kinetics in the case of weakly basic compounds if you have a gastric to an intestinal buffer stage in that experiment, and we're going to show that in the example. Input parameters you need is donor and receiver diffusion layer thickness. These are more or less defined from literature values that have been assessed. You can also look at partition coefficient in a membrane lipid phase. We use log P as a surrogate, but we have a conversion that converts log P to log membrane partition coefficient. Solubility in the receiver solution, we're assuming a full sink. These are usually proprietary buffers, and so we don't know exactly what the contents of that are. So we're, in these examples, are going to be assuming it's a complete sink of drug into the receiver solution. System parameters, membrane area, thickness, and porosity, these are defined by the membrane utilized, and the default setup is for the microdisc profiler, the microflux. So that's what we'll be using here in this case study. Output results are formulation solubility determined from drug absorption rate in terms of itraconazole model, and or precipitation kinetics, precipitation rates. The membrane dissolution options are shown here in DDD plus. On the left-hand side is the window that accompanies the settings for the membrane flux model. You can turn it on by just clicking the checkbox, and then you can set the receiver volume, the receiver viscosity, the receiver diffusion coefficient, receiver diffusion layer thickness, the donor diffusion layer thickness, membrane thickness, membrane area, and porosity. In general, you're not going to be modifying these values too much. They're kind of system parameters. Membrane partition coefficient conversion, you can convert the octanol water partition coefficient into the phospholipid membrane partition coefficient using the equation below. In the formulation composition window on the right-hand side, where you set the ingredient information, you can set the receiver solubility for the sink solution. You can set the membrane solubility. This is automatically calculated based on the log P, but you can also manually set it if you measure that. And then you can set up the diffusivities in the membrane and the receiver phase. So these are key parameters that may not be known, and so they may need to be fit to experimental data or measured with an in vitro experiment. In our flux assay, membrane assay in DDD+, we use the following set of equations that look at the drug transport through 3 distinct layers of the membrane. So there's the unstirred water layer on the donor phase of the membrane, which is where all the dissolution's occurring for the particles in the dissolution apparatus, right? So the drug will then diffuse through that unstirred water layer to the surface of the membrane, where there's a partition coefficient between the unstirred water layer and the membrane, and that's determined from the log P of the compound. The drug then diffuses through the membrane based on its diffusion coefficient in membrane and the thickness of the membrane. Where it gets to the other side of the membrane at the receiver phase, there's then a partition coefficient from the membrane phase to the aqueous phase of the receiver, and then there's diffusivity or diffusion through the unstirred water layer in the receiver phase. And these are calculated simultaneously. We're solving this as a pseudo steady state approximation, so we're not tracking the concentration in any of the membrane or the membrane or unstirred water layer compartments, which may be a limitation to the model, but seems to work okay in most circumstances. But there may be certain circumstances where the membrane loading phase may cause a lag time. So we may want to revisit this model in the future, but for now it works fairly well. Biphasic dissolution experiment, again, it's useful for the same activities as the membrane dissolution experiment. You can assess formulation solubility for amorphous and enabled formulations if dissolution isn't the limiting mechanism. You can fit precipitation kinetics if you have a multi-stage dissolution test where you go from acidic condition to intestinal conditions. Less input parameters, you just need to know the aqueous and organic diffusion layer thickness, partition coefficient into the organic phase. Log P is a surrogate for decanol, obviously. If you have a different fluid, you would have to manually enter in the solubility in that organic phase. And then the system parameters are the aqueous to organic contact area. Output results are formulation solubility determined from the drug absorption rate, and then precipitation kinetics. So the biphasic dissolution model is shown here. This is the mathematics that we use to calculate the rate of transfer between the aqueous phase and the organic phase. There's really a diffusion in 2 unstirred layers, the unstirred water layer in the aqueous phase and the unstirred organic layer in the organic phase. And then there's a partition coefficient that determines the concentration difference between the aqueous and organic at the interface. And again, the interfacial area is an important aspect. And then the driving force for the drug going from the aqueous to organic phase is the free drug in the aqueous phase that's dissolved, and then the organic concentration divided by the partition coefficient. The interface is shown on the bottom left. Again, you can just click on the biphasic dissolution and set the volume, viscosity of the organic, density of the organic, aqueous diffusion layer, organic diffusion layer, and interfacial area as appropriate. So we're also talking about precipitation modeling in this presentation. So I wanted to go over some basics of precipitation modeling. So here we're going to look at the spring and parachute diagram that we always talk about when looking at supersaturating drug delivery systems and or just gastric to intestinal transfer of weekly basic drugs, the drug becomes supersaturated in solution. If you're talking about an amorphous formulation, we can model that in GastroPlus by assuming we have a two-form solubility model now in GastroPlus where you can look at the dissolution based on the amorphous solubility all the way up to the metastable zone where it'll stay supersaturated for a given period of time based on the excipients in the formulation and how those excipients reduce crystallization. We can then model the precipitation of the drug down to its crystalline solubility via first order precipitation time or multiple first order precipitation time values, and then a mechanistic nucleation and growth model that we have built into GastroPlus and DDD Plus. We also have, and after that's completed, then you've precipitated down to your low energy crystalline form within GastroPlus. Of course, in DDD Plus, we don't have the two solubility model yet. That's probably going to come up in the future version 7 of the software, but it'll be a key improvement that we make in the next version of DDD Plus. The key variable for precipitation is the C over S or supersaturation ratio. Basic compounds with high solubility and gastric, when they're transferred to the intestinal solubility or intestinal pH, I guess I should say, and the solubility at intestinal pH, you see a high level of supersaturation and precipitation. And of course, if you have a salt form of an acidic drug and you dose that salt form, it will dissolve to its salt form solubility and then precipitate down to its free acid in the stomach potentially. So this is important for acids and bases for conventional formulations and amorphous drug forms as well. The precipitation model options in DDD Plus and GastroPlus are synchronized. So we have first order precipitation that allows you to set the precipitation time, which is the reciprocal of the exponential rate constant, and that determines the rate of precipitation. There's 3 different options for how the drug will precipitate. You can form new particles with a user-defined radius. You can grow the particles in the first bin of the distribution only, or you can grow all particles in the distribution. We then have a mechanistic nucleation and growth model that that uses thermodynamics to calculate the precipitation rate using the Lindfors model for mechanistic nucleation and growth. So that's also built into GastroPlus and DDD Plus. So for first order precipitation, GastroPlus uses a very simple set of equations that relate the rate of change of mass precipitating to basically the inverse of the precipitation time, T, and then multiplying that by the driving force in this case, which is the concentration in the luminal compartment minus the solubility. So when the concentration is higher than the solubility, based on whatever bile salts are present in the pH of that compartment, you'll start to see precipitation in the GastroPlus model. So first order process there. How people often ask, how you might obtain these first order precipitation parameters, and Kostovitz came up with this assay in 2004 where he pumped a acidified drug phase, acidified drug with dipyridamole, so completely solubilized drug into an acceptor phase at intestinal pH, a buffer at intestinal pH, and watched the drug precipitate over time. And the rate at which you pumped that drug into the acceptor phase really determined the rate of, sort of the level of supersaturation and then resulting precipitation rate. So if you pump the drug in slowly to the acceptor phase, you get a lower level of supersaturation and you get longer precipitation times, 3,000 seconds in terms of the lower flow rates of 0.5 mils per minute. When you pump all the drug in extremely rapidly at maybe 9 mils per minute in this experiment, then the supersaturation gets very high very quickly and the precipitation is much faster. And so you see a lower precipitation time of somewhere around 600-700 seconds there. Of course, we looked at a flow rate of 4.25 mils per minute, which is relevant in terms of the gastric emptying, and that's where we got our default 900 seconds precipitation time in GastroPlus. So it really only, it really only is applicable to dipyridamole And so, when you're modeling your own compounds, you need to supply a precipitation time relevant to that API. Um, so keep that in mind. We also have the classical nucleation and growth model. I don't want to get too in the weeds with theory here, but we have a full thermodynamic model of crystallization using the classical nucleation theory. We use LIN4s heavily for the derivation of this. So if you'd like to learn more about this model, I would highly suggest reading that paper. And then there's some other good publications included here as well. But basically, we're looking at the nucleation of the drug molecule. And the thermodynamics of crystallization is determined by basically the free energy of the cluster. So key parameters that you'll want to look for here, and let me use the pointer here, is the interfacial tension of the molecule. That determines how much energy, um, free energy this crystal generates as it forms, small nuclei. And when that energy is equal to the amount of free energy loss going from the supersaturated bulk solution down to a solution at its solubility limit, when those delta G's, or the free energies, are equal, that's what we call the critical radius. And that's when the drug will then, potentially rapidly crystallize and grow. And so we use this exponential nucleation rate equation based on the theory, thermodynamic theory of classical nucleation. Other key parameters involved are these log C over S, or the supersaturation ratio. So the neat thing about the classical nucleation theory is it takes into account differences in supersaturation, where the first order model doesn't. So if you dose different amounts of drug to a solution, you get different levels of supersaturation, and you have to use different first order rate constants for precipitation to model those scenarios. Well, the classical nucleation takes that into account, built into the nucleation equation. So it really takes into account different doses in vivo. So if you have a 10, 100 mg, 500 mg dose, and you want to use the same set of precipitation parameters to predict the precipitation, this model is much better at doing that because it takes into account all those aspects via the supersaturation ratio. It also takes into account the surface integration process. So this R star over R star plus gamma. So it uses this effective radius from LIN4s. And what that does is, if that value is a large value, it makes the growth of the crystal a surface integration process where it's limited by surface integration, and that could be because there's excipients around that are causing the crystallization to be poisoned at the surface. Um, if gamma is usually a very small value if there's no inhibitors or nucleation inhibitors around, and so the incorporation of the drug into the nuclei is based on diffusion to the surface only, so a diffusion limited process. We also have this exponential correction factor. This is simply like a fudge factor that allows you to fit the nucleation rate to the experimental precipitation data, right? So this model is a theoretical model, but it doesn't always perfectly predict the precipitation just a priori. You have to sometimes adjust the nucleation rates to match real data, and you do that via modification of the exponential correction factor. So it's a fitted parameter to your experimental data or your in vivo data. So now for the case study, we're going to look at O'Dwyer's paper from 2020, where he looked at the two small scale in vitro setups, in this case, the biphasic dissolution and the membrane dissolution in the pion profiler with the microflux attachment there. So looking at the dissolution of dipyridamole, ketoconazole, and itraconazole solution and capsule in these two small scale apparatus, and then looking at calculating the precipitation parameters for those compounds, and then using those for in vivo predictions within, they used Simcyp, but we're using GastroPlus in this example. I hope to show a little bit more detail than they did in their paper. They didn't really talk too much about how they or fit the precipitation parameters to the data. They used simply the aqueous data were appropriate, and then the organic concentrations for itraconazole. It didn't look like they had a full mechanistic interpretation of the all the processes going on in terms of the dissolution of the API and the precipitation and the partitioning into the organic phase or the membrane diffusion. Our model takes everything into account, and we're actually showing the full profiles that were simulated in our work here versus what they had performed in their paper. So we added a little bit more detail, I think, over the top of what they had done originally. So the dose and formulation models that we're going to look at from their experiments are, so in the biphasic experiment, they dosed diprotamol at 10 mgs, crystalline suspension, that's 2.5 mgs per mil dose because it's a 40 mil of media in the intestinal buffer. So ketoconazole was dosed at 20 mgs crystalline suspension, and that's 0.5 mgs per mil dose. That's in 40 mils of media as well. And then itraconazole was dosed at 5 mgs for this solution in capsule, and again into 40 mils of media in the intestinal buffer phase, and 0.125 mgs per mil dose there. So one thing that they did was they equalized the concentrations for the doses between the biphasic and the membrane experiment. So if you look at all these concentrations, they're the same. So what they did is in the membrane experiment, the PION microdisc profile is a smaller volume, so it's only 20 mils. So they just halved the dose for every compound to get the same concentrations in the in vitro experiment. So we can compare apples to apples in this case. All the concentrations are the same. And the dissolution setup for their experiment, they had a gastric stage for the biphasic model where they had 36 mils of acetate and phosphate buffer at pH 2. Then they added at 30 minutes 4 mils of 10x concentrated FASF version 2 with NaOH to adjust the pH to 6.8. They layered 40 mils of decanol on top of that. The area was 19.63 centimeters squared. We can do that in DDD plus by setting up the experimental phases. So, again, acetate phosphate buffer for the first 30 minutes. And then we added 4 mils of volume of the FASF version 2 at 10x concentration to get the cumulative volume to 40 mils and a pH of 6.8. We used the following buffers defined in this image for the first phase, so phosphoric acid, sodium acetate, and hydrochloric acid to get that pH 2 acetate phosphate buffer. And then we used a 10x concentrated FASF V2 with extra sodium hydroxide to account for the acid coming from the initial gastric stage. Same type of setup for the membrane dissolution, except for they used just HCl at pH 2. And again, the overall volumes are smaller. So 15 mils of HCl at pH 2 in the gastric stage. Membrane area is 1.54 centimeters squared in this case. 5 mils of 4x concentrated FASF version 2 is added at 30 minutes. And then, obviously from there, you can monitor the appearance of the drug in the organic phase. Or sorry, not organic phase, but the sink buffer phase in this case. Again, we assumed the drug is a full sink in the sink buffer. We didn't have the solubility of the drug in the sink buffer, so that was our assumption. Again, we can set up the stages as we did for the previous biphasic experiment. Hydrochloric acid for the first phase, change that at 30 minutes, add the FASF V2 4x concentrated to get to the final 20 mils of volume and pH 6.8. Again, we used the media compositions as follows in D2D plus to end up at the final pH of 6.8 when we mix those buffers together. One thing that's nice about our software is that it really does predict the surface pH or the microclimate pH at the surface of your API, and it also predicts the bulk media pH as well. So in this case, for our dipyridamole model, if we looked at the biphasic dissolution experiment that we're predicting here, we can see that the surface pH of upon dosing the free base of dipyridamole, you see that surface pH going up to about 3.5 units, and that's quite different than the bulk pH of 2.0. So we're really looking at how the surface pH is impacting the dissolution in these experiments. And then, once you transfer to the intestinal buffer stage, the buffer strength is much higher. You don't really see much of a difference between the surface pH and the bulk pH. So this is one thing our, DDD plus software is really, really good at, calculating the effects of pH and how those change over time. Okay, so now let's look at the biphasic simulation results from the O'Dwyer paper. So all the data comes from the O'Dwyer paper here, just to give them credit. Um, they have results for dipyridamole on the left, ketoconazole second from the left, and then the itraconazole solution and the itraconazole capsule are, second from the left, and the final plot on the right. So precipitation time of 396 seconds was fit to the experimental data for dipyridamole. And when we're fitting this data, we're not just looking at the aqueous concentration, we're also looking at the organic concentration. So, it's a global holistic fit to all of the data. So it may not fit the aqueous perfect, but it's, fits the organic very well. So we're, using the optimization module in the software to really try to tailor the result to best fit both of the data sets. And these are the overall parameters we get to best fit both the organic appearance data and the aqueous data. So 396 seconds, a precipitate size of 4.27 was calculated. We'll talk about that on the next slide. For ketoconazole, 2,857 seconds for the precipitation time. Now for the itraconazole solution, it's still supersaturated in the solution in the gastric media. So, but the supersaturation is much less than at pH 6.8. So we used a much slower precipitation time of 3,800 seconds, and then we transitioned to a precipitation time of 350 seconds once it transferred to the intestinal buffer at pH 6.8. Itraconazole capsule had a precipitation time of 900 seconds. So, again, that would maybe correspond to, solution is going to be higher levels of supersaturation all at once, whereas the capsule is dissolving more slowly. So you get slightly larger precipitation time for the capsule, just because there's lower levels of supersaturation in the vessel. Of course, we can do a parameter sensitivity analysis around the precipitate size to show the effects of, what would happen if the drug precipitated into different sizes. So obviously the best fit to our data is 4.27 microns on the left-hand side, but that redissolution in the case of dipyridamole is really key in predicting the appearance rate in the organic phase. So if you use a precipitate size of 15 microns, you vastly underpredict the appearance in the organic media, because the redissolution of the material is just simply not fast enough. And more so for 30 microns on the right-hand side there. So, redissolution of the precipitate is another important aspect that the model can interrogate, and you can fit with our fitting tools in DDD+. So we also, again, determined the mechanistic nucleation and growth parameters for the dipyridamole, ketoconazole, itraconazole solution, and itraconazole capsule. I probably won't go through each set of parameters. Obviously, the slowest precipitating formulation was like the ketoconazole in this instance. The itraconazole solution and capsule had higher levels of precipitation along with the dipyridamole. So the lower the parameters, or the smaller the value for the exponential correction factor, usually the higher the level of the precipitation in this case. And then, so we have our first order parameters for the membrane test as well. So on the left is dipyridamole, on the right is itraconazole, in the middle is ketoconazole and the itraconazole solution. And again, instead of an organic phase we're absorbing into this time, we have the drug diffusing through the membrane and getting into the receiver phase. Again, I forgot to mention before, the aqueous phase is the red points, the receiver phase is the green points. And then the model simulations are in the solid lines, and red for the aqueous phase and green for the organic phase, or the receiver phase in this case. The shapes aren't completely correct for the dipyridamole. We do see a lag, and this is what I was referring to earlier. Since we're making this pseudo steady state approximation of diffusion through the 3 layers, we predict that drug would immediately start appearing in the receiver phase, but maybe it takes some loading time for the drug to get into the membrane phospholipids and then to the other side of the receiver phase. So maybe we need to look into the future, and maybe in future versions look at incorporating in the kinetics of actually the drug getting into the membrane phospholipids first, rather than doing a lumped transport model across all 3 layers of the membrane. But regardless, we're able to predict precipitation times of 1429 for dipyridamole, 500 for ketoconazole, 450 for itraconazole solution, and 2300 for the itraconazole capsule. So again, the solution is precipitating much faster than the capsule. You can also see that the final concentration that the drug precipitates to is different in these models, right? Almost roughly maybe almost close to 15% for the solution, and down about 5% or so for the capsule. And that's because the amount of drug entering the receiver phase of the membrane is roughly about 3 times different, or in this case, maybe a little less than 3 times. But so to account for that difference in overall amount absorbed here, we need to really adjust the solubility of the formulation. In DDD plus, we don't have a model for the cyclodextrin yet. We have that built into GastroPlus, but since we don't have a model, I just simply adjusted the formulation solubility to match what we see in the in vitro experiment to produce the results. And then also we did this for the mechanistic precipitation model, so the mechanistic nucleation and growth model. And here we're predicting surface integration values of 0.0639 for dipyridamole. I won't go through all of these. Just again, keep in mind that the the itraconazole solution seems to be fairly rapidly precipitating, along with the ketoconazole in this case. We'll then take all those precipitation parameters for the first order for both the biphasic and the membrane dissolution methods, and we'll take those precipitation parameters and then feed them into GastroPlus and use them to predict the PK in vivo. So do an IVIVE prediction of precipitation, and this is a nice way of marrying the two software, and you really utilizing all of your in vitro data to see what may be occurring in vivo and whether or not the in vitro parameters are predictive of the in vivo results. So the first model is dipyridamole. Again, I'm not going to talk much about the parameters. We have experimental parameters for pretty much every input in the model. It's a lipophilic molecule. Log P greater than 3. We have a basic pKa that comes from experimental data of 6.3. It's low solubility, high permeability, your basic class 2 molecule. Again, experimental data for protein binding, blood to plasma concentration ratio, and we had experimental clearance value from the IV formulation from the Australian label, and we had clearance data from the Nielsen paper in 1979 that we averaged together to get an overall clearance for dipyridamole. We adjusted our PBPK model KPs, or tissue partition coefficients, by adjusting we adjusted the log P to calculate the KPs to adjust to the experimental VDSS, and then we reset the log P back to the experimental value. So here you can see that for our predictions and for the 75 meg tablet dipyridamole, again, this data was the data that was predicted in the O'Dwyer paper. So I'm only looking at the formulations that O'Dwyer did in his paper, and this data came from this Resavudi paper in 1991. So with no precipitation, you actually get a pretty good result in terms of predicting the 75 meg tablet for dipyridamole. You can maybe use an observed precipitation time of around 2200 seconds to best match the PK data. And then the best prediction that we found from the in vitro data was the membrane dissolution precipitation time of 14.29 seconds in this case. The other mechanistic nucleation and growth parameters and the other biphasic first order precipitation time parameters really didn't do a good job of predicting the Cmax and AUC, as you can see here. So it really, in the case of dipyridamole, all the in vitro parameters are over predictive. For ketoconazole, same thing, class 2 molecule, basic. We have experimental parameters for the solubility, log P, pKa, permeability, protein binding, blood to plasma concentration ratio. We are modeling the nonlinear metabolism for CYP3A4 and some PGP transport in the gut. Again, we see that when you model the 200 mg IR tablet from the O'Dwyer data, we overpredict precipitation using the baseline model. If we use the biphasic mechanistic precipitation model parameters, we also overpredicted. And in this case, the observed precipitation time was around 4,500 seconds, and the biphasic precipitation time, first order precipitation of 2,857 seconds was the best in vitro value in this case, and that's the red curve. So in this case for ketoconazole, the in vitro didn't do that bad. It wasn't too bad. Seems to do a okay, reasonable job. It does overpredict precipitation, but not nearly as bad as in the case of dipyridamole. And then finally, itraconazole for Sporanox capsule and solution. Again, we had experimental data for the log P solubilities, pKas, membrane permeability was Keiko, and that converted to a human PEF. We have protein binding, experimental data, and blood to plasma concentration ratio. We again have nonlinear CYP3A4 kinetics in the liver of the PBK model and the gut. So that's also taken into account. We can then predict precipitation or in vivo for the solution formulation, and we predict essentially no precipitation in the in vivo experiment. Maybe if you want to say the observed precipitation time is somewhere around 4,500 seconds, maybe, but none of the in vitro parameters are even close to predicting that. They all way over predict the precipitation for the solution. The closest one is the biphasic precipitation time of 350 seconds. So even the absorptive phase in the biphasic experiment doesn't reduce supersaturation ratio enough to provide parameters that are reasonable in terms of the in vitro, the in vivo response, or it's just that there's some level of physics we don't understand in the in vivo situation. So, maybe something regarding the components in the lumen that, really don't allow the drug to precipitate, or formulation ingredients as well. So again, over predicting precipitation drastically. And then for the 200 mg IR capsule, now this model doesn't really fit that good. Our itraconazole model is based on tons of different PK data from many different data sources. So, our model was trained to globally fit a wide variety of different IR capsule data from different studies and publications. And so for this study in the O'Dwyer paper, it doesn't work that great. The Cmax is pretty good, but the Tmax and AUC maybe is a little off. But nonetheless, it allows us to see whether or not the precipitation times are accurate. And in this case, they are over predicting precipitation as well. But the membrane dissolution test, in this case, precipitation time of around 2,300 seconds seems to do the best. Not great, but certainly better than some of the other results we had in terms of dipyridamole and the itraconazole solution. So, it was a mixed bag here, hit or miss. Some of the precipitation parameters were somewhat close to what you'd see in vivo, but all in all, they, generally overpredict the precipitation in vivo. And that's what we've seen for the vast majority of compounds when we're modeling in GastroPlus. Over and over again, for all the compounds we've ever looked at, we tend to see overpredictions in precipitation using the in vitro parameters when doing IVIVE. So this is no different, this result here from the O'Dwyer paper. So conclusion is DDD plus provides complex models to handle membrane dissolution. We also can handle biphasic dissolution, and Also, if you look back 1 year ago, you can look back at our artificial stomach duodenum test uh, results for pioglitazone, where we show that the precipitation of that compound is also overpredicted using the ASD test. So look into that, go back and look at that. Uh, go back and look at that result. So all these complex models do not seem to provide in vitro precipitation parameters that are predictive of the in vivo precipitation. So this is why we say IVIVE is challenging for all complex in vitro tests. Precipitation is best optimized to experimental PK data in our current understanding. The in vitro tests are good to provide valuable information on propensity to crystallize, and any formulation solubility enhancements or any formulation additives or excipients that may reduce crystallization. These tests are very valuable for that kind of information. But in terms of in vivo predictions for precipitation, they tend to be very poor in our experience. And hopefully in the future, we will crack this nut, I guess you could say, and really improve our IVIV predictions for precipitation. So that's all I had to go through today. I wanted to thank you very much. And I think my colleague Vera Lukachova will be taking questions. And I thank you very much for um, visiting our talk today. Thank you.
Okay, if you have not already done so, you may send written questions for Dr. Lukachova using the questions pane on your control panel. Vera, let's get started. The first question here says, regarding the media buffer pH, does the simulation account for the API pKa values to calculate the microenvironment and bulk equilibrium pH values? Vera, are you there? I think you may be on mute. Can you hear me? Can you hear me now, Vera? Sorry, there are some technical difficulties.
Hopefully you can all hear me. Jasmine, if you could send me a message to see if you can hear me. For some reason, my audio is not working again. I will be reading out the questions. Apologies for this. By the time I finally fixed my audio to hear the recording, something happened with the audio to be able to hear Jasmine. So I'll be reading out some of these questions that you've sent out. I'll try to answer as many of those as possible. So I'll just go down the list. Regarding the media buffer pH, the question was whether the simulation accounts for API pKa values to calculate the microenvironment and the bulk equilibrium pH values. So yes, DDD plus does include a model which accounts actually not only API pKa values, but also pKa values of the buffer components. So it is a dynamic process that does take into account all of the different ionization aspects and equilibria when calculating the surface pH and the bulk pH as a response to the dissolution of the API. The next question is sort of a follow-up on this. What was the latest version of DDD Plus available with surface pH feature? The latest version of GastroPlus, or current version of DDD Plus is 6.0, but I think the surface pH or the microclimate pH calculation has been there since at least version 2, maybe even 1. So that feature, the microclimate pH calculations, has been in DDD Plus for a number of years now. Another question is related more to additional or other type of link between to predict in vitro and in vivo dissolution profiles backwardly from in vivo PK data in humans. So this is a different type of application or a link between GastroPlus and DDD Plus. The way the examples that Jim was describing in the webinar were more going from analyzing the in vitro dissolution data in DDD Plus and then feeding those parameters into GastroPlus to predict what would happen in vivo. Another route of utilizing these two programs together is using GastroPlus to deconvolute potential in vivo dissolution profiles based on PK data, and then use these profiles within DDD Plus to either help you design the formulation better, right, to change the formulation to get closer to the desired in vivo dissolution profile, or help you design the experiment, right? Help you create a design in vitro dissolution experiment that would lead to more accurate or more straightforward IV-IBC. And so those two programs actually can work both ways. There is another question regarding to absorption processes happening in vivo, right, simultaneously with the possible precipitation processes and how these are accounted for in DDD Plus. Right? I think this question was in the meantime answered in the subsequent slides, or in subsequent examples, but just to reiterate, right, this is all dependent on the in vitro dissolution experiment setup. The DDD Plus now does include variety of different conditions and setups, and if the in vitro experiment was created or was set up the way that it accounts for that absorption or simulated absorption or removal of the dissolved compound from the dissolution media, right? Which the examples that Jim was presenting were biphasic dissolution or membrane dissolution experiments where that absorptive phase is included, right? In that case, the model does account for the interplay between the compound moving into that absorptive phase and precipitating as well. So the capabilities there, it is all dependent on the experimental setup. Another question on general on DDD Plus, whether it has any use for IV or any other non-oral drugs. So DDD Plus is created more as a general tool for simulation of variety of in vitro dissolution experiments. So from that point, it can be applied to non-oral drugs as well. In fact, one of the latest additions that was added with the last version of DDD Plus was a mechanistic model for long-acting injectable products, and to account for the differences or for how the polymeric particles, PLG particles, would be degrading and so on, and simulating that in the in vitro experiment. So if you have non-oral drugs or that where you are exploring in vitro dissolution experiment in any of these more common assays, you would definitely be able to use it in DDD Plus as well. Another question was on the log-P, that log-P is used in the model calculations and whether log-D would not be a better parameter rather than log-P. So that both GastroPlus and DDD Plus do include built-in models to calculate log D versus pH. Right? So depending on what experimental value we are able to find in the literature or get the measurements for, we can enter into the program as an input either log P or log D at specific pH. And the program is then able to use the built-in model to calculate log D at a specific pH depending on what is needed for a specific model application or part of the simulation. Okay. And I think that's all we have time for, so I'll pass it back to Jasmine.
Thank you, Vera. Thank you to those who submitted questions. And if yours was not addressed, we will follow up via email. If you missed any part of this webinar, visit our website at simulations-plus.com for an on-demand replay. This concludes our webinar for today. Have a great day. Thank you.